Well, I hope you had a wonderful lunch. If you all wouldn't mind going towards your seats, we are needing to resume. It is 1 o'clock. It's actually 1:01 according to my cell phone. So we're trying to be as prompt as we can be. All right. Thank you so much for making every effort to be back here on time. We give all of you gold stars. Thank you. All right, so we will begin with the afternoon session. So again, hope you all enjoyed catching up, making some new connections over lunch. I'd like to welcome our session presenters. Our next session is on flooding from increasing high rainfall events, and we have Peter Sheng, Alaa, and Charles Jacoby. Dr. Peter Sheng is Professor Emeritus and Adjunct Research Professor in Coastal and Oceanographic Engineering in the Civil and Coastal Engineering Department of the Engineering School of Sustainable Infrastructure and Environment at the University of Florida. Dr. Sheng received a PhD and a master's in Fluid and Thermal Sciences from Case Western Reserve University, as well as a bachelor's in Mechanical Engineering from National Taiwan University. Dr. Alaa is a civil engineer at the South Florida Water Management District who has made significant contributions to water management and restoration projects, including Everglades restoration. Dr. Alaa holds a PhD in stochastic modeling and optimization from Utah State University and earned his undergraduate degree from Cairo University. Dr. Charles Jacoby is the Strategic Program Director for the Florida Flood Hub for Applied Research and Innovation at the University of South Florida. Dr. Jacoby received his bachelor's and master's degrees in biological sciences from Illinois State University, a doctorate in biological sciences from Stanford University, and a master's in business administration from the University of Western Australia. Remember, as we did this morning, that Menti will be open throughout these presentations for you to enter your questions as they come to mind. And with that, thank you.
Thank you, everyone. It was my pleasure to be here, and I appreciate Jennifer and CHNEP for organizing this wonderful conference. I had many excellent talks this morning, so I'm going to do my share right now. Compound flood drivers and nature-based protection. And we talk about compound flood because all the flood drivers have been increasing, not just rainfall. In fact, the average rainfall in this region, annual average, daily average rainfall has not really increased over the last 50 years. Now, what's been increasing is the days of extreme rainfall, as you see on the left side of the slide. Gorda and Naples and Fort Myers, the days with more than 3 inches of rainfall has increased from 4 to 6, in some places 4 to 8. So that's a big increase, and usually it accompanies with hurricane. And so how do we deal with this compound flood? And how can we modify our currently known FEMA 1% flood maps, coastal maps, create compound flood maps, help the community to prepare, and options, not too much, but I'd like to mention the sponsors for various projects, including NOAA, 2 programs, and EPA, and as well as Collier County and City of Naples. We have acknowledged our team members on some of the research project, Coombe project, and Mike Savarese from FGCU is here. We also work with USGS and South Florida Water Management District. And so let me go on to the next one. Okay, it works. And so what I want to say is that these different flood drivers, sea level rise, hurricane, surge and wave, and rainfall, as well as other issues have been rising over the years. The sea level rise is projected to become 14 to 18 inches high by 2060. So that number may be a little bit on the higher side. Intense because of rapid intensification, as we saw in all the recent hurricanes, Irma and Ian, Michael, Helene, and that caused great disasters. Hurricane-induced wave have been increased by 20% in the last decade. Hurricane surge have increased by about the same amount in the past decade. There's some good papers on those topics. Rainfall, as I said, the number of intense rainfall days have increased by 50%. The average rainfall has not increased that much, but the future extreme rainfall is projected to increase by 5 to 55%. So all these create more flood risk, and we need to produce compound flood map. Any flood map that includes more than one driver is called a compound flood map. And also the stormwater system is becoming outdated and overwhelmed because of all the developments and sea level rise issues. People are looking into looking at the future compound maps and looking at these nature features like oyster reefs, which might reduce loss by 5 to 50% if you design them correctly, put them in the right place, and mangroves as well. You can use them to reduce the flood loss, and I'll touch upon those, and we have papers coming out describing how to evaluate the value of these nature-based features in reducing flood loss. So Mary mentioned that this rainfall events is a highly spatially dependent. Just like Hurricane Ian on the left, you saw the track. On the right side of the track, there's a little rainfall, but on the north side of the track, there's a lot of rainfall. So quite different. And in fact, in Punta Gorda, it supposedly had a 1,000-year rainfall. But the 1,000-year rainfall also happened in Helene, not in here, but in Asheville, North. That dark red spot was a 1,000-year rainfall that caused a major disaster flooding there. And then on the right in Texas, Cavill storm, that's not even a hurricane, at a 1,000-year rainfall caused the flood. So yes, rainfall is important. So FEMA flood map doesn't include them in the coastal flood map, so how do you deal with it? That's where the compound flood map comes in. So I'm going to describe this compound flooding, because it means it has more than one driver. Storm surge, rainfall, groundwater, each one is a different driver. So coastal flooding, and typically, FEMA has coastal flood map, and you can create inland map for a 1% rainfall event, and you put them together. And the more correct way is you consider these coastal, fluvial, pluvial flooding, and produce the compound flood map. Did a paper in 2022, look at the compound flood due to combined sea level rise, storm surge, and rainfall in Southwest Florida. And there's a link, but I don't want to click because I may not be able to come back because of this thing. So what it shows that by 2100, the compound flood, the total inundation volume in Southwest Florida may increase by a factor of 2 to 6. But there's a lot of uncertainty by 2100. It may change. So I want to go through 3 examples, actually 2 examples, because the third one is something that Florida Hub and FDEP is doing using the statewide, feather model. So I'm going to talk about 2 examples. One is what we did in Collier County with the NOAA support. We created a tool for adaptation planning called ACUN. ACUN stands for Adaptation of Coastal, Urban, and Natural Ecosystems. And Mike is the co-PI with me on the project. And then we recently, FDEP, Resilient Florida program in Dixie, Jefferson, Taylor, DJT County, not to be confused with the other initials. But so 2 examples I'll go through. The main focus is how do we do compound flood map? And how does compound flood map compare to coastal or inland flood map? And what does it mean in the real hurricane? Okay? working in a real hurricane, so I'm going to use some examples in Ian and Irma to talk about that. And how do we do the current and the future projection? So we've done all that stuff, and then we have come up with a method to assess the value of natural-based features to reduce flow loss and using validated models validated with the local data. So these are the drivers. On the left is the fluvial flood and the coastal, and then we produce the compound flood map on the right. So I'm going to give you examples. How do we reckon with these processes, produce a compound flood map rather than just a coastal map or an inland map that looking at the river flooding only. So pluvial basically refers to the rainfall, and fluvial is like the flow over land and through canals and things like that. Okay. And so the first example on the Akun project, and we actually used 4 different models, not just one model. And if we do the FEMA flood map, we just do one coastal model. The coastal model is CS3D SWAN model, which is a 3-dimensional and mangrove resolving, vegetation resolving model. We can incorporate the horizontal distribution and vertical structures of marshes, trees into it. So supposedly, if we have the data, SWAN is a wave model, these are dynamically coupled. On the watershed model, South Florida Management District has developed a nice BCB flood model. Because based on the MICA model, they produce the flow in the canals, discharging into the watershed, and from based on 100-year or 1% rainfall event. Then on the urban stormwater in the model domain, you can see we have inside, we have a smaller red 4 subdomains. The second one from the top is the one in Naples that has complete stormwater system resolved by this Flow 2D model, which is a contractor of South Florida Management District. Then we work with USGS who has developed a mangrove migration model, a warmer mangrove, okay? And so we couple these models in order to produce the compound flood. And so we look at the interaction between mangroves and hydrodynamic, salinity and accretion of sediments, all that is included in the model. And then we feed into the Flow 2D model our 1% flood elevation from the CS3D model is completely fed into the watershed model, and then they input from the BCB flood. So there's quite a bit of a model coupling. And the goal is to produce probability flood maps. For the coastal map, we follow the joint probability method with optimal sampling. Sorry, this gets a little too technical, but at least there are no equations here. So, and unless you want to see them. So we use this probability method so we can come up with about 350 synthetic storms that represent the past climatology in this region, not the entire Florida, but in Southwest Florida. And so for the future, we use these future storms predicted by climate model. And in this case, we use the CAN ESM with downscaling by WRF model. So we get the future storms more intense, predicted for 20 and 2100. Then we can also calculate the loss of structures based on our flood elevation, basically the FEMA damage assessment model. So we can calculate the economic loss with and without mangroves and assess the value of mangroves in different census tracts of the county. And so we create the 1% flood maps for all those scenarios on the lower left corner from now all the way to 2100, the sea level rise. So look at the 1% compound flood map. Again, we produce a coastal map with a 3D model. Then we use a Flow 2D, produce a inland model, inland flood map. We combine the two, produce these. The one on the left is 2025, one in the middle is 2060, 2100 is on the right. But 2100, as I said, it's highly uncertain, but doesn't look very promising, all right? The one in the middle is interesting. In subdomain 2, not ICPR, the Flow 2D resolved the stormwater system. But by 2060, whether you run it with the stormwater system or not, it doesn't make much difference. That means the stormwater system becomes outdated by 2060, something to consider. And so here is an example we did within the Big Bend using resilient Florida funding. And as we look at this region, we have the FEMA map and the Army Corps South Atlantic Studies map. And they look, FEMA map shows more flooding on the side, on the coast, and Army Corps is a little more inland. Neither one has really done inland flooding considering river flow and rainfall. So we did a multivariate copular model. We look at a compound flow of 3 drivers: rainfall, storm surge, and river flow. We divide it into 3 different regions based on the watershed of rivers in the system. And so these are for Jefferson and Taylor and coastal water level and rainfall. And so 2-driver copula shows that those 3 red contours, the one in the middle is the 1%. 1%. Okay, so on that curve, we can pick 9 events or something and simulate the flooding. Using a HACRAS model, we can produce a compound flood map. But for Dixie County, we had to consider 3 drivers, try copular model, and we use 9 scenarios to produce a compound flood map. So then we produce this compound map, we combine with 2 other coastal maps to produce a truly compound flood map. So this is the integrated map based on 3 maps. So I'm giving you examples how we do things differently in Collier and here. It's really depending on where you are. It's very difficult to come up with a unified way to do a model for the entire state of Florida. In our opinion, we have 12 regions, and we will have to look at a local watershed, how the river, rainfall, coastal surge interact in different ways, looking at 100 years worth of data, do a statistical analysis, come up with this copula, and then run a model simulation. So it's not a one-size-fits-all operation. And so doing statewide model is a real challenge. And so these are the 2070 with different sea level rise scenarios, intermediate low, intermediate high. So, and this has been accepted by the Resilient Florida program. We actually did a whole slew of vulnerability assessment on all the infrastructures, as well as adaptation plan. The last but not least, and this is just a paper, just came out. So we show Ian and Irma, they have very different tracks. They create different losses. Irma because it mostly over land, didn't do that much coastal flooding. But Ian on the right create a lot of flooding, which is in percent of the property within each of those neighborhood octagon. The two on the left is the 1% flood damage, flood level, and then second one is on the damage percent. The one on the right is interesting because these are the return period maps. So you look at the Irma return period map, the flood at every single location falls within the 100-year flood elevation. But for Ian, it's up to 10,000-year return period, okay? And in this county, it didn't look good. And Sanibel actually is 10,000 year. I didn't show it here because I focused on Collier. That will be another paper. But you get to 1,000-year return. And so what does it mean to damage? To cut it short, the loss, flood loss during Irma is more like a 100-year event. So what's the total loss on the lower 200 million or so, okay? During Ian, the loss is about $2 billion, okay? structural loss just due to flood, not wind. We can't, and these estimates are validated with the FEMA NFIP. Unfortunately, even though people in these regions are more proactive, the penetration ratio, that means the percent of residents flood NFIP insured, is about 46%, which is, you compare it to Louisiana, 20%. But so you can only compare. So we had 2 billion loss. Half of that is NFIP insured. If we compare our estimated loss with the actual FEMA loss data, which they provided to us on a contract we cannot disclose, but that we got a very good fit. The R square is about 0.71. So it's a very good agreement. So the loss calculation is validated. The loss points to a 3,500-year event, not a 100-year event. So what does that mean? Is 100-year flood map sufficient? I don't think so. So somebody mentioned that this morning, risk tolerance, right? Mary mentioned about a risk tolerance approach. If you think you can tolerate, you can use 1%, but you can't afford to lose your property, you might want to do what a 1,000-year flood map, not a 100-year flood map, okay? And the 100-year flood now is not going to be a 100-year flood map in 2050. Okay, so right now, it might look like a 1,000-year flood map. It might look like a 200-year flood map by 2050. So in summary, we need to consider that 1% map may not be adequate planning, all right? And so I'm told to stop. And so we need to produce these maps. Again, we need to do this regional approach, and I think we can achieve that. There's something have to consider that when you do the statewide flood map, you need to consider these regional maps that incorporate all the detailed data that are available out there, validated with NFIP damage data. These are something that's hard to do on the statewide basis. For the foundation to your effort in developing the statewide flood map. And nature-based protection resilience, unfortunately, I don't have time to go into it, but I have another paper coming out soon. So I have a question. How much do you think mangrove is worth in reducing flood loss per hectare? I'll give you three numbers. $30 or $3,000 per hectare. That's your wish, right? It's more close to 30. But we're fighting some reviewers right now. We'll have a paper on that. But during Ian, mangroves reduced the flood loss by about 20%. So that was good. It's worth to restore, but you got to be careful. You got to know where to put the money at, and so is the oyster reef. And there are a lot of people talking about oyster reefs. The companies popping up here and there. They tell you can put oyster reef in your backyard, but don't believe that until you see a scientific study. And there is a real benefit over cost. Okay, thank you.
So should I start? Okay, this is Dr. Alaa with the South Florida Water Management District. Today I'm going to be talking to you about rainfall cluster trend analysis or trend and frequency analysis. I will be basically, I'll do the best I can to manage within the time because the materials are a lot, even though we cut back many of the slides. Nicole was give you guys an idea of our resiliency program. She's one of the resiliency team. I don't know what is the next slide. Can you move me to the next slide? Okay, so yeah, so Nicole, so let me just go ahead and and give you the topic. Basically, at the South Florida Water Management District, we have a lot of we have extensive network of rainfall data that the area itself of the district is partitioned into 14 rainfall basins. They are called operation and maintenance basins, and these basins they have no any hydrologic significance. Frequency analysis conducted over those 14 basins do not always give any coherent characterization of rainfall behavior. So please next. Yeah. So of interest in this study is say, you know what? Yes, we have conducted extensive frequency analysis and trend analysis over those 14 basins. Now we need to explore areas that they are grouped by natural commonalities, if you will. The study conducted across rainfall from 1935 to 2024, and the extreme rainfall thresholds are 4 inches, 4.8 inches, and 6 inches, and the spatial clustering using DB-scan. And basically, the idea is now we have extensive data sets. How can we characterize them or delineate boundaries around them that are consistent with some sort of natural behavior of rainfall, natural coherent behavior? And next. Shouldn't be saying this. Okay, the DB are basically the abbreviation of it is basically density-based spatial clustering of applications with noise. In a nutshell, it is some methodology that tries to look for some coherence or some coherent characteristics of certain zones and say, you know what, within that zone, all the data set within that zone represent some sort of a coherent pattern of rainfall. The parameters of that methodology, I would call it minimum exceedance and minimum points and epsilon. And basically, let's say we have 400 data points, and those 400 data points, each point has time series of rainfall from 1935 all the way, they say, to 2024. So we identify the number of points beyond that they are exceeding certain threshold. If you remember the previous slide, we said we're going to do this for 4, 4.8, and 6 inches. Therefore, how many points above that threshold is minimum exceedance? And this is one of the parameters. The other parameter is, well, what is the number or data points that they are meeting that exceedance condition to form a cluster? So cluster is basically number of points. Each of these points or time series have that minimum exceedance or more data points. E or epsilon is the maximum spatial distance to minimum points. So in other words, we have to identify a radius of search, and that radius of search will look for data has minimum points. Now, there are two parameters in the clustering methodology, DB-scan, something called core point and something called border point. Core point is basically has the minimum exceedance and minimum points and within the span epsilon. But border point is just a point around the boundary of that cluster, but is not part of the core points. Next. Okay. Oh, shoot. Hold on. No, I think I skipped it. So next slide. Yes, sorry. Next slide. So what is the procedure of that methodology? Basically, all grid cells exceeding the threshold, let's say 4 inches, are extracted, right? So grid cells with the minimum exceedance, which is minimum exceed points, are retained, also known as exceedance cells. Then DB-scan groups spatially adjacent exceedance cells into contiguous rainfall clusters. Each cluster is assigned a unique ID and analyzed separately. See that in the map refers to, we call it noise, where basically these points fill nowhere. They are in the middle of nowhere, therefore they are not picked. Next, please. Okay, the strength of the DB scan is that captures irregular cluster shapes, not constrained to fixed windows, identifies both persistent and emerging hotspots. We're gonna see that once we see the maps. Robust to noise and non-clustered outliers. So any points they don't belong to a particular pattern are excluded from this study. The limitation of these methodologies vary with parameter choices. And we had to go through a lot of trials and errors in a separate effort, where basically we eventually were able to identify the number of exceedance points, a number of minimum points that give us meaningful pattern of those clusters. The result is that each dbScan cluster generates a time series of exceedance counts, maxima, and mean intensity used in further trend frequency analysis. In a nutshell, just to understand what maps we are trying to apply the dbScan to identify certain boundaries. These boundaries include within it some points on the map, on the data or the data network. Each of these points have minimum number or more of exceedance that we have along the time series. So if you have time series from 1935 all the way to 2024, we say this, we say, okay, we were able to get 17 bigger than the minimum exceedance, and then we include it. If time series has only 3 or 4 data points, which is less than maybe the minimum exceedance, then it's excluded. Next. So daily rainfall data aggregated into threshold exceedances, we said that, right? So basically we say, you know what, if it is below the threshold, it's excluded. If it's above threshold, it's included. Okay, because we are really concerned about bigger values, bigger storm, bigger events of rainfall. dbScan parameters, which is the epsilon of search, minimum exceedance, which is the exceedance cells, and minimum points, which is the minimum number of cells included in the cluster. For each cluster, daily peak over threshold rainfall time series was constructed. Next, please. So this is an example, for example, that we have here, this is the footprint of the South Florida Water Management District's area. You have, if you guys are familiar with the area, you're going to see the East Coast, Lower East Coast, Upper East Coast, which is to the right. I have Big Cypress basins to the left, and then we have the Everglades cluster, which is the yellow ones. If you see those ones, you have here 1, 2, 3, 4, basically. So this is basically a natural dbScan results for peak over threshold, which is POT equals 4 inches. That's very natural and very interesting that the dbScan was able to capture rainfall pattern which aligns, the boundaries align with those basins, which was interesting. And when between 35 and 2018, which is the previous analysis that happened back in 2020, and when we did the same for the new data set, when we extended the data to 2024, basically we found no difference. Next, please. Okay, so what we have here for each of those clusters 1, 2, 3, 4, 5, 6, when we data was all the way to 2018, look at the black line, it stops at 2018. We saw no trend whatsoever when the peak over threshold. Slide more, please. Now, when we added those 6 years, look what happened. Cluster 4 and cluster 6, if you go back to the map, you will realize where they are. Cluster 4 and cluster 6 shows a trend, okay? And that trend is because the last 6 years were really wet years. That's for the peak over threshold equals 4 inches. So all these data points represent data that are more than 4 inches. Next, please. When we did the same, but for the cluster, it changed a little bit, but still the same for the older period of record and the newer period of record. Next, please. Okay, so here, when you did the 5 inches, as you notice, we have no trend whatsoever, okay, but we have definitely less dense data sets because the higher the value of rainfall, the less number of data available. So now if you move to the new period of record, which is 24, please, next slide, please. For 24, we did not, could you please toggle between the 2 slides just to show you guys the difference? Yeah, see, all what you see is just extension of the line of the period of record, but there was no any change in the trend for the 5 inches peak over threshold. Next, please. Now this is for the 6-inch threshold. When you increase the 6-inch threshold, we saw something a little bit interesting. When we applied the dbScan, we found out that the shorter period of record, which is we found 13 clusters. If you move please to the next slide, there is a slight change between the two, which tells me yes, clusters can change once the data is exactly. If you toggle between the two, you're going to see a little bit variation between the two ones. One has 13, one has only 10. So next, we're going to see now the results. So for the results, for the peak over threshold, look at the lower right corner. That's where the peak over threshold of 6 inches. You're gonna notice that you have a trend over cluster 1. Please go back 2 slides. Yes, one more. No, this one. Cluster 1 is the big cypress. Is the one the lower left corner of the map. Please go further again, forwards, forward, more. The second one, yes. But now when we moved to the again, that appears on the lower right corner, you can see that the cluster of 1 has disappeared, but then we have different cluster which is 4, 5, which is cluster 4, cluster 6, and cluster 8. No, cluster 6 and cluster 8. Those, yeah. So basically, cluster 4 and cluster 6 have trend. So you can tell that, of course, with 6 more scarce or less data, and you see also the trend changes from an area to another. And I'm going to comment on that at the end. Next, please. Okay. This will bring me to the conclusion and recommendation. And here I have to take my time, since I have time list for the during this presentation. I wanted to go fast first, and then we start giving you guys the recommendation and the benefits and the power of cluster analysis. When we use multiple thresholds to identify both chronic and acute rainfall zones, one of the benefits of the cluster analysis. Recent data alters cluster structure. Period of record matters. Now, someone tells me, wow, so now we have trend. Does it make sense that only 6 years will show you a trend? I tell you, don't really get carried away. That's exactly the point. Sometimes we see things are trendy, but when more data get available, you don't see a trend, and vice versa, which tells me that we are somehow lying on a frequency wave, because anything in hydrology is basically superimposed parts of signals. So if you are in a signal that's eventually going to go down, but right now you are in the increasing or rising portion of the signal. And the beauty of the signal of the cluster analysis, it has secluded, or it has identified clusters with a coherent natural pattern of rainfall, and it tells you, listen, you are in that area, in that trend, in that time you are facing an upward trend. Maybe it's 20-year trend, but because of what we're about to see, something called chronicle points and emerging points, supporting adaptive infrastructure and resilience planning using these insights. Basically, now we know that some areas will be faced with increasing trend of rainfall above certain thresholds, and that's where the adaptive strategy that you would really use to deal with this kind of adversary, very important and a big interest of the resilience officer. Cluster analysis needs to expand in a similar way. The OMD basin-based analysis, that's basically, we have come long way with the OMD operation and maintenance district basin. We have to do the same thing for the cluster analysis. Next, please. Okay, persistent versus emerging clusters. That's one of our discoveries of this cluster analysis, that we need really to keep clusters appear across both 1935 2008 to 2018 and 1935 to 2024. If you guys remember those slides that showed you the map of the clusters, okay, when the clusters remain the same, it means that we are dealing with persistent clusters where it needs certain type of resilience studies or trend analysis or frequency analysis. Okay, these clusters indicate geospatial zones with long-term exposure to heavy rainfall and emerging clusters. And those emerging clusters basically, yes, only in 1935, if you notice that, likely reflect recent rainfall intensifications post 2018. We have seen that moving from 2000, from 35, 18 period of record to 35, 24 period of record, those 6 years have introduced what we call emerging clusters, new clusters that require special attention. Reports recent changes in rainfall behavior due to climate variability or urbanization. Next, please. So threshold influence on spatial footprint. At 4 inches, many clusters are spatially diffused, covering larger areas. At 6 inches, clusters are compact, located over known heavy rainfall zones. This threshold filtering helps distinguish chronic versus acute flood risk zones. Planning should treat low threshold clusters as broader vulnerability zones and the high threshold clusters as acute hotspots. This is, again, one of the techniques that they are vital, really, for any resilience-related studies for rainfall. More in-depth cluster analysis is needed to address the above issues. Next, please. Impact on risk communication. What does it mean? In newer period of record suggests increased hazard frequency. That's not a brainer. Increased spatial density of clusters may overwhelm infrastructure in new locations. Also, this is not a brainer. That's also so clear things to the water manager and decision makers. Updated cluster maps provide a data-backed communication tool for stormwater and resiliency planning. Clear visuals. That's something now, our recommendation for the managers. CDFs and histograms enable dialogue with raw rainfall data. Do I have more or just that's it? Risk, again, is it the last slide? Maybe it is, right? So let me, yes, of course. If I had the chance to present, I basically, I hope that Nicole was here to kind of give you guys an idea of how the district is handling the resilience in general. But there is always non-stationarity in our system, and the non-stationarity is what triggers. It's very important element on the frequency and trend analysis for resiliency. And this is something that we should really develop deeper understanding for it. But I have always seen cluster analysis to be a key to understanding the severity of rainfall and the plan accordingly. And I think I'm done.
Okay, good afternoon. I'm between you and the break, so I'm here to provide some context and introduce you to some modeling that we're undertaking to yield estimates of changes in rainfall. So let's first just kind of orient you to the Flood Hub. So the Flood Hub is a strategic exercise as we get out ahead into the future. Supports the Resilient Florida program in increasing resilience across the state. And the graphic shows you a little bit about the Resilient Florida program and what it does. So it provides funds for planning and implementation, it curates data for the state, and it helps folks develop these proposals. A key focus of all this is flooding, and the Flood Hub addresses that by organizing groups of experts who will take the best available data and tailor it to Florida. In essence, the Flood Hub is there to help level the playing field. So when grants are awarded, it's based a lot on vulnerability, and the data from the Flood Hub are meant to provide everybody with some data that they can use. As it says there, though, it's not prescribing or proscribing what you use. If you have a justification for using other estimates of threat, you can use those. You just have to provide that justification. And so, again, one of the key targets you've heard a lot of. So one more time, what is compound flooding? So as you know, as sea levels rise and coastal surge, storm surge, and so forth increases, that pushes water onto the land, coastal inundation, and high rainfall, inland and near the coast produces water that's trying to get off the land, and the two collide. You get compound flooding, and that can include groundwater appearing at the surfaces. So That magnitude is important, but as was pointed out by Peter, the likelihood is also really critical, and you're looking at the likelihood of two extreme events, and that's a fairly complex thing to calculate, but it can be done. The graphic here gives you an idea of someone's effort to do that, where you have the increasing chance of compound flooding going vertical, and you have the increasing surge and the increasing rainfall driving that. But it's a nonlinear sort of likelihood that'll. So one of the first things that the Flood Hub addressed was sea level change. That's one of the key elements of estimating compound flooding. And that was done with a work group that used the data from the 2022 report that you heard about earlier this morning. In that federal report, they, as often happens at the national level, take Florida, and the East Coast goes up with the Carolinas, and the Gulf Coast goes with the Gulf states. So what this work group did that underpinned that report and try to excise the data for Florida and get an estimate just for Florida. And the graphic helps you see why that is. So that blue line at the top there, that's the total change in sea level that's estimated. Then below that is the global average, that's the sort of yellow line. And then below that is the oceanic component of the total change in relative sea level. And then as you heard again this morning, vertical land motion is another component. Well, that's the purple line at the bottom. The vertical lines span Florida, so Pensacola on the left and over to Jacksonville on the right. And the key probably take-home message here is that if you excise those Gulf states in particular, you alter the total change in sea level. And if you look at the span for Florida, the blue line that's between those two vertical lines, you'll see that it's very close to the global average change in sea level. So what the work group ended up with was basically for change in sea level around Florida. And does that matter? And it turns out that it does. So if you look at this particular graphic here, that's comparing two of the scenarios. So you heard a little bit about the scenarios. All of this is driven by what you expect emissions to be like, changes in global temperatures. So the intermediate low and intermediate are the two most likely scenarios given the current state of affairs. And this graphic I'll use for sea level rise with what was in that federal report for the two regions, right? The Eastern Gulf, well, the one main region, Eastern Gulf. And as you can see, the Flood Hub estimates are lower. And those inches actually can matter in terms of costs. So the other key element of compound flooding is rainfall. And there's a work group that's working on what we call change factors, which are applied to design storms. So water systems, they use design storms, which was talked about a little bit. So the y-axis is the depth of rainfall that you have in inches in this case. The x-axis is duration, goes from minutes up to days. And then the different lines are the different return intervals for storms. So the longer the return interval, the more extreme the storm is. So these change factors exist. They're used all the time. What the work groups tried to do, we're going to take data from the global models that predict the changes you might expect to see. The key thing is as the atmosphere warms, it holds more moisture, which can drive heavier, more intense rainfall. And it takes these global models, and the outputs of these are then statistically downscaled to apply to the stations that are around Florida. These are called Atlas 14, in this case, stations. And those have long-term records of rainfall. And so the data that's appropriate for those, then taking the data from past modeling and future modeling and comparing the two, you can generate a change factor, which is how much the rainfall is expected to change in the future. And apply those, then you take the change factors and apply them back to the design storms to adjust your engineering for out to 2050, 2070, 2080. So there's a whole range of things you have to consider. One is the time horizon you're shooting for. So this graphic is change factors for 2070. The other thing is the duration of rainfall that you're looking at. In this case, it's 7 days of cumulative rainfall. Change factors are on the y-axis. The dot is the median change factor. So that's the middle of the distribution of change factors that the models comparisons produce. And the bars show you the 17th and 83rd, gives you an idea of the spread, the uncertainty that surrounds that median. And then along the x-axis are 3 different forcing scenarios. In the old days, it was done just solely with changes in radiative forcing, but now the global models are trying to go back into emissions pathways, how much CO2 is emitted. And those are SSPs, shared socioeconomic pathways, and they get more extreme as you go from left to right. So that's and then the 5 to 500, those are the return intervals, so more intense storms. So the overall change here, the overall predicted change in rainfall is somewhere between a change factor between 1.05 and 1.15. That's the range of the medians. That which means 5% to 15% more rainfall for any given kind of storm. Okay, but the statistical downscaling is something that people get a little concerned about. That doesn't, which we've heard a fair bit about, as Peter pointed out. You get regional dynamics that drive rainfall. And so the next steps for the rainfall work group are to go back to those global climate models, and then we'll try to use other modeling techniques to bring this down to the spatial scale that we're looking for. So the global models work on a 1 degree latitude, 1 degree longitude grid, and that's pretty coarse. Florida would sort of be in a grid and a half, maybe. Small areas very well with these global models. So what they're trying to do with this modeling exercise is to capture the local effects. So the sea breeze effects and lake effects, the sort of change you get with urban and rural land cover, as well as the kind of things you get from coastal geometry, and then the nearshore oceanic features. How do those affect the rainfall? At the same time, you don't want to lose track of the larger scale drivers that are in. And the way we're going to do that is to couple models. So we take the output from the global models, use it kind of as, I'll call it boundary conditions for lack of a better term, for these other models. So the first downscaling effort is using a community Earth system model, which brings that down to like 24-kilometer grid for atmospheric stuff and 10-kilometer grid for oceanic. And then the graphic shows you what you can see. The difference there is in the CMIP6, as we call it, the global comparisons, versus the community Earth system model on the right. You can begin to resolve things like the Gulf Stream and the loop current and some of these other features that are going to affect rainfall. Then those outputs from that modeling are the boundary conditions for the next step, which is going to take it down to about a 10-kilometer grid. And that's the regional spectrum, regional oceans model system. I think it's just trying to show you that bringing this down to a smaller scale helps resolve some of the biases that might occur in the larger scale. So on the left are observations of rainfall, and you might just note the green areas in particular. In the center would be the output from that community Earth system model, and on the right is this effort with this new modeling using those boundary conditions. And you can see that the green areas start to appear, and they're about in the right spot. Then outputs that are the boundary conditions for the next step down, which is done with the weather research and forecasting model. That gets you down, we're probably going to settle on about a 4-kilometer grid, because smaller grids have been a little problematic. The graphic will show you on the left, it's going to show you the predicted rainfall. The center is going to show you soil moisture responding to that rainfall, and the right part of the figure will show you temperature. As the rainfall passes, the temperatures get cooler. So again, you just keep trying to draw to smaller and smaller scale. So what's the key to the whole thing? Very much like what talked about using the statistical approach. So you have these models do a reference period so that everybody can check that their models are in sync, validate them as it were. And then they'll do, that's the historical ensemble to the reference period. And then there'll be at least 2 warming exercises. On a warming is yet to be agreed on. Probably going to be somewhere between 1 and 3 degrees out to 2100, because that's the kind of trajectory that's being predicted at this point. Then again, process the data to extract the extremes in rainfall, because that's what you're interested in. Peter talked about the peaks over a threshold, right? Set a threshold and look for rainfall over that threshold. And you generate the change factor much like you had before. So again, we'll just do a different approach. And what does this all translate into? Well, higher sea levels, more intense rainfall, increased risk of flooding. That's pretty obvious to everyone. A lot of threats from increased flooding to lives and livelihoods. And the magnitude and the likelihood both are needed in order to make sensible plans and responses to these things. And then the tailored estimates to Florida should help us safeguard lives and property. Invest wisely, so again, you're not over-engineering, kind of have the Goldilocks solution, and then prepare for the future.
All right, we're going to now go into Menti. If you haven't put in your question already, feel free to do so at this time. And we're going to turn over and start looking at the questions. And I hope our virtual presenter can see these as well. But basically, we're going to take turns asking you some questions, and perhaps multiple presenters might want to chime in on some of them. Feel free to do so. So we have some questions about, have you ever used AI in any of this modeling and analysis? Why or why not? Anyone have any comment on that one?
So is this a general question, or is it only for someone of the presenters?
This is all, any of the presenters can answer these questions. So if you have a comment.
Yeah, actually, this is a $1 million question, and we can spend a few hours answering the question, really. AI is something that I sincerely recommend that every agency and every entity, university, the place of research, they have to invest a great deal of time to understand how they can utilize it. And my biggest recommendation always, use AI as your assistant and do not use it as your expert. Do not use AI as your expert or advisor. That is a rule of thumb, first of all. If you go and ask AI to give you an advice on your field, then you probably don't know how, you don't understand the what the AI is made for. You have to recognize the difference between assisting you with something and guiding you or leading you to do something, especially in the area of research. There are a lot of areas, a lot of ways to utilize AI to even write small scripts for you, or to help you out with strategizing something that you have already put. So for the research, that is the attitude. For even writing a document, that's the attitude. AI, you should always consider your mindset or attitude towards AI as the AI is helping you out, assisting you, but not to advise you or to lead you in what you're doing.
Thank you. Any other comments on that?
So one of the challenges for looking forward is you don't have data from 2070 to apply AI to. You can apply it to the output from the models. One of the debates that the working group on rainfall had was, is there any pattern to change factors across the state? And AI might help us to look at the results to see that. But again, you need to generate that information for the future.
All right. We have a question about what percentage does the 1,000-year event equate to per year? So like 1 in 100 is a 1% chance. So is it just the same with the 1,000? It would be that percentage. And then do you have any comments? I mean, I think that is something we run into a lot, that people have a hard time conceptualizing when we talk about a 100-year event, a 200-year event, a 500-year event. And then, of course, that is more based on historical data. And then, as you mentioned, looking forward, that's going to change over time. So could you have some comments on that to help people understand how all that relates to any given year, what their probability of risk is?
Yeah. So 1% year flood is really not a good terminology. It seems to imply once it happens, it won't happen another 100 years. It's totally wrong. Because if you go to FEMA website, they don't use the term 100-year flood anymore. They use annual chance exceedance probability of 1%. There's a 1% chance annually that the flood elevation of certain values, say 2 feet, might be exceeded in your location. In fact, if you type in your address, you should be able to find your 1% flood elevation on FEMA website. They should. At least if you live in Collier County, if you use the Akun tool we set up, by the way, it's public, Akun public version. You type in address, it'll give you the 1% flood elevation at any address you type in. In fact, it will give you the 1% flood elevation from now until 2100, and it changes, it will increase. So 1,000-year flood is actually annual chance 0.1%. Okay, and that's what the Dutch use for permitting, planning, adaptation. They don't use 1% flood. They use 0.1% flood map for adaptation. That's how they can survive, because the entire nation is below sea level. All right. So 1% flood can happen more than once every year, can happen this year, next year. And like I said, Ian was if you look at the flood elevation in some parts of Collier County and Lee and Charlotte County, they're 10,000-year event. So that's 0.01 annual chance. All right. It can happen. When does it happen? We don't know. Like this year, we haven't had any. We haven't had any 1% flood anywhere in Florida, coastal flood. So they're independent, so they can happen this year, next year, and they can have, Puerto Rico got hit by 2 Category 5 hurricanes in 1 year, in 1 season. So these are all totally a random event, and nobody has control of.
Yes, and that's again why calculating likelihoods of some of these things, is an important factor in terms of looking at your risk tolerance and how you're going to do your engineering.
Yeah, I heard somebody say that if you're planning to live in your house 30 years, then it's a 30% chance that the flood could hit sometime while you're in your house. And I think that changes people's thinking when they think that way versus hearing 1%, which sounds so minimal risk.
Yeah. Can I make a very important comment here as a stochastic modeling expert? One thing that we, the experts, have yet to succeed. We have failed so far is to put the concept of statistics into layman language that we communicate to the layman. A lot of people don't know what it means by 1% chance or 0.5% chance or 5% chance, because an event, when it happens, it has 100% chance. So, and people won't even know that, okay, so what does it mean by 5% chance? And I think the bottom line is that statistics are made to be able to have some sort of quantification for random events over a cumulative number of years. And when we reflect back on on the past 10 years or past 20 years and we start characterizing events, that's when we say, yes, that event belongs to a 100-year event or even more. In fact, every 10 years when data become available, all these numbers will change. And that's why it's important to quantify the uncertainties around any of these likelihoods. And we should be able to convey that in a layman language, and it's still challenging.
So we have another interesting question here about, are certain geographic areas more prone to experience these clusters? How do we reconcile that with the expectation that Florida will become more arid with climate change?
That's a beautiful question, and I'll be completely arrogant if I tell you I know the answer fully. And yes, there's a lot to be done in that area and on the local level and getting even counties and cities involved. As we said, there is an emerging and chronicle clusters that it evolves over the years as data become available. And definitely it's something that the resiliency, by the way, resilience program in our district, they are like our client. We provided only the frequency and the trend analysis, and we basically are giving guidance how to use this for adaptive management. And definitely those who have that question, I would highly recommend that it should be directed to the resiliency team because they are the ones who are looking into this. But yes, getting the people involved at the local level is very important. And how to do it, it's a strategy that needs to be put forth.
So there's a question about, are there any concerns about the continued availability of data for these models? Especially, I think people have been hearing in the news, some things are coming offline. Do you find any challenges with having the data you need to continue to build out and utilize these?
At this point, no, but again, it's hard to tell exactly where things will end up. They may be a little harder to get at, but I think they're likely to still be there.
Okay. What is the timeline for the flood hub model and outputs to become available for use?
So that whole process is scheduled for about 3 years from now at this point.
And another one is, what do you mean nature-based protection, wave-induced flood loss? But not surge-induced loss. Couldn't nature-based solutions help to protect surge-induced loss?
Good question. That's a good question. I think that's directed at me, unless you want to take it.
No, it's all-
So, well, first of all, waves are, you can see they're wave induced. Those are driven by wind. Hurricane wind produce very high waves. And the wave periods a few seconds, right? And a really short wavelength. You can see the wavelength, one wave breaking after the other. And mangroves, things like mangroves, oyster reefs, can be designed to dissipate those waves using the tall structures, dense structures, dissipate the wave energy. And they can dissipate wave quite efficiently. As long as you have the rule of thumb is you need to have enough mangrove behind the shoreline. I say about the size of the football field, right? Everybody watches football. So the size of the football field, mangroves sufficiently tall, like in Naples, 10 meters, 50 meters tall mangrove, they can dissipate about 2/3 of the waves with that design. Okay. However, surge is a different animal. Surge is long wave, just like tides, very long wave, long period. And when it comes to the mangrove, the whole shoreline and tens of kilometers inside, the whole thing is like a bathtub. So the wavelength is many, many tens of kilometers, right? So just a football size of the mangrove is not going to dissipate surge, all right? Wave, tide is not going to break, surge is not going to break like the wave does break. So how long do you need to have the mangrove to dissipate surge? I say 10 kilometers worth of mangrove. Where do you find that in Florida, along the coast of Gulf Coast? There's no place where you can find 10 kilometers worth of mangroves so you can dissipate surge. And then unfortunately, along the Gulf Coast, most of the loss, flood loss that we calculate comes from the surge. It's not from the wave. Even though the mangroves are very effective in dissipating waves, they can reduce more than 50% of the wave loss, but not enough of they can only dissipate about 10% of the surge loss. All right? But that's why I say I don't like to use the word NBS because that implies nature-based solutions, as if you solve the problem of flooding. It doesn't. It offers some protection. These are nature-based features for flood protection, only partial flood protection, but not solution. The NBS is getting overly used. It is a very optimistic, proactive term, but I don't like to use it personally. Okay. So.
We're coming short on time, so let me ask one last one. How does the data back up the anecdotal belief that increased precipitation intensity is happening within the past several years? Do you see that manifesting in the data? I know the data set would be shorter, obviously, if it's just the recent years, but has anyone looked at it to see if there's things changing more recently? Dr. Lee, that might be for you.
Okay, say it again, please.
Does the data back up the anecdotal belief that there is increased precipitation intensity that has been occurring in the past several years?
Well, we can't. Okay, okay. We have done few trend analysis over the years, and based on my experience, I have seen this going up and down. So sometimes, like for example, the last 6 years of data, when we added them, some areas where they experienced downtrend, they experienced no trend, and some areas who experienced no trend, they experienced upward trend. So sometimes the data gets shifted geographically, but overall, from my experience, really, I don't believe that an overall trend that's for sure that has been consistently observed over the past 30 or 40 years, it doesn't exist. But can we have a trend over a decade or two? Yes. Did I answer the question?
Yes, yes, that's
Okay.
wonderful. And we're now going to go to a break. So if you